Welcome to this new virtual lecture brought to you by the Jordan IEEE ComSoc and SBS joint chapter. Today's lecture is titled, Is Noma Efficient in Multi-Antenna Networks? Given by the IEEE ComSoc Distinguished Lecturer, Professor Bruno Klerks. As it always the case with the distinguished lecturers, they have an long, impressive bio, which we try to shorten here for the sake of time. Dr. Bruno Klerks is a full professor, currently the head of the Wireless Communication and Signal Processing Lab and the deputy head of the Communications and Signal Processing Group within the Electrical and Electronic Engineering Department at Imperial College in the UK. He received the MSc and PhD degrees in Applied Science from the University Catholique de Louvain in Belgium in 2000 and 2005, respectively. He was with Samsung Electronics in South Korea, where he actively contributed to the 4G applied research. He has authored 2 books, which are MIMO Wireless Communications and MIMO Wireless Networks, 200 peer-reviewed international research papers, and 150 standards contribution, and is the inventor of 80 issued or pending patents, among which 15 have been adopted in the specifications of 4G standards and are used by billions of devices. He was an elected member of the IEEE Signal Processing Society SPCOM Technical Committee. He served as the editor of the IEEE Transaction on Communications, the IEEE Transaction on Wireless Communication, and the IEEE Transaction on Signal Processing. He is currently an IEEE ComSoc Distinguished Lecturer. We are very fortunate today to host a veteran in both theory and practice. Thank you, Professor, for joining us today. You have the floor now.
Thank you very much, Sami, for your kind introductions and for your kind invitation. So let me share the screen again. Right, so this talk is about non-orthogonal multiple access. It's about 2 things. It's about the important question of whether non-orthogonal multiple access, which has received quite a bit of attention in the past few years, is efficient in multi-antenna networks. And the second aspect of this talk is about looking at next generation multiple access techniques and what actually the key, I would say, properties that we may see in next generation multiple access techniques. So this talk is based on a recent paper that is published in the Open Journal of the Communication Society with my co-authors here that has the same title, essentially. Right, so you're all familiar with multiple access techniques. This is not new, but this is an important topic in communication. And it comes from the fact that wireless communication systems are inherently multi-user. And so the big question that we have in multi-user system is how we can serve those multiple users in the most efficient way. And in the context of multi-antenna networks that is nowadays prevalent a bit everywhere, how we make use of those multi-antennas in the most efficient way when we have multi-user setting. And so in communication information theory, we know that there are 2 fundamental building blocks of multi-user channels, is the broadcast channel and the multiple access channels. Very simply, it refers to the downlink scenario here on the left side and the uplink scenario there of a single cell. And so multiple access techniques refer to all types of techniques that make use of the resources to serve multiple users, and those resources could be time, frequency, power, antenna, code, and so on. And so in this talk, we'll mainly talk about the antenna domain, and the power domain will come into play as well. We'll not talk too much about the code domain. And we will focus on the downlink settings, even though some ideas are actually transferable to uplink, but the emphasis will be on downlink here. Right, so what do we know from information theory when we have multiple antennas at the transmitters, and we have multiple users. And so represented by this scenario here, where we have M transmit antennas, for instance, and here we can have K single antenna users. I assume single antenna here for simplicity at the receiver. Right, so if we have particular case where M is equal to 1, so we have single antenna nodes everywhere, we know for a long time that actually the channels here, H1 to HK, they become scalar, and they can be ordered according to channel strength. And therefore, there are two known capacity achieving strategies when we have Gaussian channels. One is superposition coding with successive interference cancellation, and the other one is dirty paper coding. And so superposition coding with SIC here is something that is known for 50 years and has received quite a bit of attention in 5G and in the academic literature nowadays under the name of non-orthogonal multiple access. Now, when we move to multi-antenna settings, so whether we have a MISO setting, multiple transmit antennas and single antenna at the receiver, or the MIMO where we have multi-antennas everywhere, users, the situation becomes a bit different because users cannot be ordered according to the channel strength anymore because the channels are matrices or vectors. And so we know that applying SCSIC or superposition coding with SIC would lead to a performance loss. And we know that actually SCSIC is not capacity achieving anymore when we have multi-antenna settings. And so the only capacity achieving strategy that is so far known is dirty paper coding. Now, we have to keep in mind that this is known under specific some assumptions, which is the knowledge of the channel state information is perfect at the transmitter. So all those channel state here, H1 to HK, so the channels of user 1 to user K, is assumed to be perfectly known at the transmitter. In that case, we know what is the PC's capacity achieving. In the scenario where the CSI is imperfectly known at the transmitter, then it remains an open problem. We don't know what's the capacity of multi-antenna, multi-user, multi-antenna communications when we have imperfect channel state information at the transmitter, and we don't know what's the best communication strategy that we could come up with. Right, now DPC is not really used in practice because it's relatively complex. So what has been used in 4G and 5G is actually some form of multi-user linear precoding that is popular under the multiple access of space division multiple access. So I will talk about this in a moment. Right, so what has been very popular in the past few years is to classify multiple access according to this notion of orthogonality versus non-orthogonality. So we have on the left side, we have orthogonal multiple access, OMA, and we know many instances of OMA, TDMA, FDMA, CDMA, OFDMA. Those are all different types of orthogonal multiple access and has been used extensively in 2G all the way to 5G. And the key idea there is simply to eliminate any multi-user interference by allocating orthogonal radio resources, whether it's in the time, frequency, code domain, or joint time and frequency domain. If we move to the other extremes, which is the non-orthogonal, then we try to use the power domain to break the orthogonality, and by using this superposition coding with successive interference cancellation. And so the way it works is the following. If we have a transmitter with one antenna and I have two receiver here, let's say single antenna receiver, and I want to deliver, the base station here wants to deliver two messages, one to user 1 and one to user 2, and want to deliver those two messages in the same time and frequency resources. So how we do that, we superimpose the two messages in the power domain, and we ask one of the two users, typically the strong user, the one with the stronger channels, to fully decode the message of the other user. So for instance, here in this case, user 1 would be the strong user, and user 1 will decode the message of user 2, and then cancel the contribution of that message to its received signal, and then decode its own message intended to itself. On the other hand, user 2, what it will do it will see the interference from user one message and will simply treat it as noise. And so we know that from information theory, Noma is better than OMA, especially when you have this disparity of channel strength among users. Now, what's the key here in Noma is that one user fully decode the message of another user. So you can think of this as one user fully decode the interference that has been created. And so we'll see that in terms of interference management, this is a particular type of interference management where any interference is fully decoded at the receiver. Right, so this is non-orthogonal multiple access. Space division multiple access is another type of multiple access that really focuses on the spatial domain and relies on multi-user linear precoding to form beams and to transmit a message in each of those beams. And this has been extensively used in multi-user MIMO, network MIMO, millimeter wave MIMO, massive MIMO throughout 4G and 5G. And the way it works is the following: you have K messages, you encode those K messages into K independent streams, you linear precode them. Those precoder creates essentially different beams that carries every time one message. And at the receiver, each receiver will decode its intended stream by treating any residual interference as noise. And so each of those receivers here, user 3, may see some interference from user 2 and user 1 message, but it will treat it as noise at the receiver. So it has a relatively simple receiver where any interference is treated as noise. And so we start seeing some difference here between the different multiple access techniques. In OMA, you really try to avoid any multi-user interference by orthogonalizing resources. SDMA, you treat any residual interference as noise. And in NOMA, you try to fully decode the message of other users. So you try to fully decode interference. Right. Now, what if you combine, in a way, NOMA with multiple antennas? And then you have this notion of multi-antenna NOMA. And so what can be done there is essentially having multiple antennas, for instance, at the transmitter, and we have multiple users, and we group users into, or we pair users into different groups. For instance, I have group 1 here, and in each group, I perform superposition coding with successive interference cancellation. So what that means is that each group here could represent, for instance, one beam, or maybe a set of beams. But importantly, in each group, one of the users would have to decode the message of the other users. So user 1 here, for instance, would have to decode the message of user 2, user 3, all the way to user G. And the number of groups could change. You could have only one group, or you could have multiple groups. Right. Now we know that if you do that, you would have that NOMA is superior to OMA. So this is relatively easy to show in general, or at least would have the same performance. Now, what is less clear is whether you still have gain over using SDMA, for instance, right? Because SDMA also uses multiple antennas, but does not pair users into group and does not enforce a given user to decode the message of other users, right? So what we show in this paper is that doing that is something that we have to be very careful. It's something that has been done quite extensively in the past 5, 6, 7 years in the literature. But what I will show here is that if you force a user to decode the message of other users, this could lead to an inefficient use of the multiple antennas of the transmitter, and you lead to an inefficient use of the SIC receiver. So we have to be very careful with that. And I think this is actually the theoretical background why ultimately in 5G, NOMA was investigated as a study item, but was not further pursued as a work item because the gain was not shown convincing enough. Right, now we have other type of multiple access that has not been discussed in standards. And the one I will talk about is rate splitting multiple access, which has some commonality and differences with NOMA, also commonalities and difference with SDMA, and also operate on multi-antenna settings. And so what I will show here also is that this framework of multiple access is actually a very general framework that encompasses SDMA, NOMA, OMA, and other form of transmissions as special cases, and was developed completely independently and in parallel from this NOMA literature. But the key property of that multiple access is not to fully decode interference or not to fully treat interference as noise, but to partially decode interference and partially treat interference as noise. So we'll see, we will try to compare OMA, SDMA, NOMA, and RSMA and try to identify really the benefit of NOMA over in multi-antenna settings on one hand, and the key features that we may expect for next generation multiple access. So those are the two important questions I will try to answer. And to do that, what I will do, I will not compare NOMA versus OMA. This has been done extensively in single antenna setting. We know the answer for the last 50 years. Has been done extensively for multi-antenna settings as well. But as I said earlier, when you have multiple antennas, you don't have only NOMA versus OMA. You have other types of schemes that you can come up with. And the most popular one would be SDMA as used in 4G and 5G. So it's very important that we really contrast multi-antenna NOMA with SDMA and other types of actually multiple access techniques or multi-user transmission strategy that could be developed to fully identify the benefits of multi-antenna NOMA. Right, so one of the metrics I will use is the notion of degrees of freedom, DOF, also called multiplexing gain. And I will use this as a relatively simple metric to try to assess the performance of the system before we go into more complicated simulation and so on. And so when we design the systems, what we try to do first is to identify a good metric. And so the classical metric in communication is to maximize the rate, and you can have multiple metrics. Either you want to maximize a per user rate, or you want to maximize a sum rate, so the sum of the rate of multiple users. For instance, here, the sum of the rate of all those K users you have in a cell, for instance. Or you can have a weighted sum rate where each of those rates is being weighted, or you even can have maximizing the minimum rate. So you want to maximize the worst case, the worst rates among all those K users in a cell. So that could be different metrics. Now, if you increase the SNR, then you can approximately write your rate as something like this. The rate of a given user K essentially is a prelock factor here, dk, which is we'll call DOF, or multiplexing gain, multiplied by log2 SNR. And so this dk essentially tells us how fast the rate will increase with the SNR. So it's the number of interference-free streams we can transmit to user K. And it's the slope, effectively, of the rate versus the SNR. And so we want the slope to be as high as possible. And so, for instance, here, if I have two users, K equal to 2, and I have two transmit antennas, and I have two different transmission strategy, one in blue and one in red, what we would prefer here is the red curve or the red strategy, simply because the slope of the rate of the red curve is higher than the blue curves. And so essentially, the rate will increase faster with SNR with the red strategy compared to the blue strategy. And so a higher DOF, at least, it seems to be more attractive because the rate ultimately at higher SNR will increase faster. Right, so let's go back to multi-antenna NOMA and the particular case of MISO-NOMA, multiple transmit antennas, but single antenna at the receiver, and just two user case. So that's the basic building block, but you will see that from these basic building blocks, you will understand most of the issue. If you have two users you want to communicate with, and you have two messages, W1 and W2, respectively intended to user 1 and user 2, what you do in NOMA, you encode them in such a way that you create two streams, S1 and S2, and linear precode them. Now, those streams are created in such a way that one of those two streams is decoded by both users. And so, for instance, here, I will assume that user 1 decodes the message of user 2. So how do we do that? Well, user 1 here would have a receiver equipped with successive interference cancellations, where user 1 will first decode the message of user 2, will re-encode it, cancel it from the received signals, and then will decode its intended message W1. And so it will perform essentially SIC. User 2, on the other hand, would see any interference from user 1 message. So user 2 will see interference from S1, but will just treat it as noise. And so it will decode his own message without doing any form of SIC. And so the order which one decodes the message, this could be changed, right? Sometimes user 1 has to decode the message of user 2, sometimes it's the opposite. Now, if you do that, then you can calculate the rate of user 1 and you can calculate the rate of user 2. And so the rate of user 1 is very simple. Assuming you have perfect SIC, is just a log2 1 plus some form of SNR. And the rate of user 2 is a bit different, because the rate of user 2 it comes from the fact that user 2 message is decoded by both users. It's decoded by its intended receiver, user 2, but is also decoded by user 1. And so we have to make sure that the message of user 2 is correctly decoded by both users. And that's the reason why it is transmitted at a minimum rate that is equal to the minimum between the rate that is supportable by the channels of user 1 and supportable by the channels of user 2. And that's the reason why we have those two, a min between those two logs. Right, so let's take that and let's calculate simply the sum rate of that system. So the sum rate of that system is just, I take those two rates and I sum them up. And because I have a minimum, I can take any terms here in that minimum. Any term would be larger than the minimum. And so I can always upper bound the sum rate as the sum of this term that comes from the rate of user 1. And this term here is simply one of those two terms. It's actually 1 plus A here. Right, so I can arrange this, and what I end up with is this. And what does that tell us? Now, what you see here is say that the sum rate of Noma, Noma, is essentially upper bounded by this quantity. Now, what is this quantity? This is the sum rate of an effective two-user single antenna, so SISO, multiple access channel. Why? Because the user 1 here, the user 1 that is here, what it does, it acts as a receiver, and it sees two messages coming to itself. It sees W1 and W2, and it decodes both messages. So actually, user 1 acts as a receiver of a two-user multiple access channel. And this is indeed the sum rate of a two-user multiple access channels, where the effective channel now is denoted by these pre-coded channels here, H1P2 and H1P1. So this is quite important, because we know from information theory that if you have a single antenna at the receiver here, and you have a receiver that acts as user that acts as the receiver of a multiple access channels that has a single antenna at the receiver, your degrees of freedom will be limited to 1, because you have only one receive antennas. And this is really what we see here. We can further upper bound this and show that actually this is smaller than log2 1 plus the norm of H1 multiplied by P. And so what is this? This is simply the rate you would have got if you do OMA, orthogonal multiple access. So from this expression, you can see two things. On one hand, you can see that your sum rate of Noma is no larger than the sum rate of OMA. So there is no benefit in having Noma when you look at sum rate. And you have, instead of having and you have a multiplexing gain or degrees of freedom that will be equal to 1, because here you transmit on effectively one interference-free stream in the system. Right, so how can we compare this with SDMA? No, just as a summary, I just said that we have 1 degrees of freedom here, so our sum DOF will be equal to 1. And so we can calculate the max mean fair DOF, which would be the slope of the minimum rate among the 2 users, and we can show easily that the best maximum max mean fair DOF would be equal to half. Essentially, the sum DOF would be split equally among the 2 users. Now, what would we get if we do 4G, 5G techniques, SDMA based on simple zero forcing beamforming, for instance? Well, if we have multiple antennas here, we have 2 users, we encode W1 and W2 independently from each other, and we just ask each receiver to decode their respective messages. And if we do that, well, you can transmit 2 interference-free streams. You can transmit with a multiplexing gain, a sum multiplexing gain that is equal to 2, and each receiver would actually get 1 interference-free streams. And so what you see here is that you would get a sum DOF with SDMA that is twice as large as what you get with Noma, even though you have a receiver that is much simpler. So that raises a lot of doubts about what's the benefit of multi-antenna Noma, and about the design principle and the potential, because you increase the receiver complexity, but you see that your rate here, your sum rate, will actually increase much slower than what you would get with SDMA. Right. Now you can extend this whole discussion to the K-user scenario, and you can take multiple antennas at the transmitter. You can break this into multiple groups. You can have 1 groups, you can have G groups. It does not really matter. The key property here, what you have in Noma, is always that in each of those groups, one of those users will decode the message of the other users. So this is what we had here. In this case, we had the user 1 decode the message of the other user here in the 2 user, but you can have this in the general case where user 1 decodes the message of G-1 users. And so what you can do is you can calculate the sum rate of the messages in each of those groups. And so you can write, for instance, the sum of the rate of the users in group 1, so this is expressed by this, will always be upper bounded by this quantity. And what is this quantity? This is the sum rate of an effective single antenna, SISO, single input, single output, multiple access channel, where the receiver of these multiple access channels is actually the user that decode the message of all the other users. So for instance, here would be user 1, for instance, it decode the message of all the other users. So again, user 1 acts as the receiver of an effective SISO multiple access channels. And so if you think about that, that means actually the sum DOF of this group will be at most 1. The sum DOF of another group will be at most 1. And if you have G group, you can expect that the sum DOF will be at most G. And that's the reason why the sum DOF will be equal to the minimum between the number of transmit antennas and the number of groups. So if you have only 1 group, well, your sum rate will just increase with as log2P, log2 SNR, despite the fact that you may have many antennas at the transmitters. Right. Now, how does that compare with simply doing space division multiple access or multi-user linear precoding, multi-user MIMO, classical techniques? Well, we know that actually you can transmit a minimum between M and K. And so if you compare that with what we had here, G is always smaller than K when you do Noma, because obviously once you start pairing users, the number of groups will always be smaller than the number of users. So what you realize here again is that your sum multiplexing gain or sum DOF of a K user Noma is actually always smaller than what you would achieve with simple space division multiple access. And you would do that here without any need for any SIC. So Noma would incur a sum multiplexing gain loss at the additional expense of an increased receiver complexity. Right, so in my view, the whole notions of orthogonal versus non-orthogonal is really not the problem. After all, if you look at SDMA techniques or multi-user linear precoding, you could argue this is already a form of non-orthogonal strategy, because you transmit in the same time frequency resource, you transmit message to multiple users, and those multiple users interfere with each other in general. If you use MMSE precoding, for instance, or regularized zero forcing precoding, even if you have perfect channel state information at the transmitter, the message will interfere with each other. So users interfere already when you have SDMA techniques. So in my view, the real problem is how the interference is managed. And that's where you really see the difference between the different multiple access techniques. OMA, there is no interference because you orthogonalize the resource, so you have one user per resource. SDMA, you try to treat any residual interference as noise. That's what you do at the receiver. Noma, you try to fully decode interference. One user has to fully decode the message of the other users. And so what we know from information theory is, from the work by Ed King-Tse and Wang in TIT 2008, is that the strategy you use depends on how strong the interference is. So if you are in a weak interference regime, we know that treating interference as noise is good. If we are in a strong interference regime, we know that fully decoding interference is good. If you are in a weak interference regime, but you try to fully decode interference, we know that actually this is not good. And inversely, if you're in a strong interference regime, but you try to treat it as noise, that will not work well either. So what you need to do in order to bridge those two extremes is to partially treat interference as noise and partially decode it. And so we can use this to try to compare SDMA and Noma and these other multiple access techniques, RSMA, and we can qualitatively understand that, well, SDMA treats any residual interference as noise. That means actually should work well whenever the interference is relatively weak compared to the noise, and will not work so well if the interference becomes more significant. On the other hand, Noma will probably work better if the interference is strong, but it will not work so much if the interference is weak or medium. The RSMA, on the other hand, will try to partially treat interference as noise and partially decode it, so it will bridge those two extremes of interference and will be able to flexibly manage the interference according to essentially the interference level. Right, so rate splitting multiple access is a general, flexible, and robust multiple access techniques. It's general because we'll see it encompasses SDMA, OMA, NOMA special cases. It's flexible because it deals with any interference level, and is robust because it's inherently robust to imperfect knowledge of the channel at the transmitter. And the idea builds upon the notion of rate splitting that was introduced for the single antenna interference channels by Carlyle and Han and Kobayashi in 40 years ago. But it's been revisited in recent years, not for the interference channels and not for the SISO case, but more for the broadcast channels and the multi-antenna case. And so we'll show that RSMA is actually a way to bridge SDMA on one hand and NOMA on the other hand, by partially decoding interference and partially treating it as noise. Right, so let me show you how this RSMA works for a two-user example again, and how it connects to SDMA and NOMA. And so here we have, again, two messages, W1 to user 1, W2 to user 2, and I have two receivers, user 1 and user 2. The receiver for user 1 is actually the same architecture as for user 2. So user 1 and user 2 will use an SIC receiver. And so what we do here is that we take those two messages, and instead of encoding them directly into two streams, S1 and S2, what we do is that we split them. So we take the message of user 1 and we split into two parts, WC1, WP1. This is what is written here. And I do this for W1 and W2. So I take some bits and I split into two different parts. And so I take those two parts here and I now combine them and I create a new messages that is called WC. And so what we have is from two original messages, W1 and W2, now I create three messages, WC, that will contain some information from user 1 and user 2, WP1 that contains information for user 1 only, and WP2 for user 2 only. And then I encode them independently from each other here into 3 streams. And so from 2 messages, we now create 3 streams. SC is denoted as a common stream that carries information potentially for both users, but importantly, this common stream will have to be decoded by both users. And then we have S1 and S2 that are called private streams and carry information only intended to you, respectively, to user 1 and to user 2. And so any interference between S1 and S2 will treat it as noise, and SC, on the other hand, will be decoded by both users. And so once we have those 3 streams, we linear precode them, and we have now the system model where we have PCSC, P1S1, P2S2. And at the receiver, both user will decode SC by treating S1 and S2 as noise, and then perform SIC, where user 1 here will decode SC, perform SIC, and then retrieve S1. And from SC and S1, it will retrieve WC1 that is intended to user 1, and from S1, WP1 that is also intended to user 1. And from those 2 sub-messages, it will recombine them into W1. So it will retrieve the 2 parts that were split here. It will retrieve them back at the receiver. So this is called rate splitting because the rate of a given user has now been split. The rate of user 1, part of the rate of user 1 comes from the rate of S1, and the other part comes from a portion of the rate of SC that relates to WC1. So a portion of SC carries the WC1, and so a portion of the rate of SC will contribute to the rate of user 1. Right, so where is Noma, where is SDMA here? Well, SDMA is simply obtained by, if I have this system model here, SDMA will be obtained by turning off the common stream. So how do we see this? We have the common stream here. Well, if I simply turn it off, then that means actually my message W1 has to travel to S1, and W2 has to travel to S2. So I simply encode W1 into S1, W2 into S2, and I have my conventional system model P1S1 plus P2S2. So no power is allocated to SC. Where is Noma here? So keep in mind again that Noma is obtained by having one user decoding the message of the other user. So if you do that, that means that the one message is actually decoded by both users. If one message is decoded by both users, it means that that message is effectively transmitted as part of a common stream. And this is exactly what Noma does. Noma turns off one of those private streams. So for instance, turns off S2, encode W1 into S1, and then encode W2 into SC. And so this is what I have here. W1 goes into S1, W2 goes into SC. You see the difference with SDMA. W2 goes into S2, while here W2 goes into SC. That means that if W2 is in SC, W2 is now decoded by both receivers. And so we have a signal model that is PCSC plus P1S1. S1 carries W1 and SC carries W2, such that W2 is decoded by both users. This is exactly Noma. And so you see from this that SDMA and Noma in this 2-user example is just particular instances of this rate splitting framework. Right, another way of looking at that is looking at the mapping from messages to streams. And so what I said earlier is that we have 2 messages, but now in general we can have 3 streams. And so the question is, how do you map those messages to those 3 streams? And here we have those 3 streams, 3 data pipes. And for SDMA, I take W1, W2, I just map them into S1 and S2. If I have Noma, one of the messages go into S1, the other message goes into SC. If I have OMA, I have only one message that is transmitted. If I have multicasting, effectively, you could put both messages into the common stream. And if you have rate splitting, you split the messages such that part of the message of the W of user 1 is here, the other part is there. Part of the message of user 2 is here, the other part is there. And so what is important is the way SC, S1, and S2 are treated. SC is such that anything that falls into SC is decoded by both users. Anything that falls into S1 and S2 will be treated as noise by the other users. So anything, if you transmit anything on S1, essentially S1 will create any interference to user 2, and this will be treated as noise at user 2. Anything that is transmitted into S2 will be treated as noise at user 1. And so by adjusting the content of SC, S1, and S2 and the power location, essentially you can bridge SDMA, NOMA, OMA, multicasting, and you see that the rate splitting is just a superset of all those multiple access techniques. Right, so what does that mean to split the messages? Well, at the bit level, it simply means that, for instance, here, if I have 4 bits for user 1 and 3 bits for user 2, for instance, I can take the first 2 bits, will go into the common part, the last 2 bits would go into the private part. And then for user 2, for instance, I take the first bit would go into the common part, the last 2 bits go into the private part. And then from B1 and A1, A2, I can construct the common message. And so here, for instance, I would have 3 bits that would map to 8 PSK symbols, for instance. And then for the private stream, I would have, for instance, a QPSK symbols carrying those 2 bits and a QPSK symbols carrying those 2 bits for WP2. And so what the receiver would do, user 1 would retrieve WC1, WP1, so would retrieve those 2 bits from the common streams, would retrieve those 2 bits from the private streams and recombine them to create the original message. But now you can expand this to the K users. This is an example for the K user. And essentially what you do here is that you have K messages and you split those messages into a common part, a private part, and from K messages, we now create K plus 1 stream, 1 common streams, and K private streams. And so each receiver here will decode the common stream, will perform SIC, and then will decode its intended private stream. And so you have a system model where you have this part here that is reminiscent of what we have in SDMA multi-user linear precoding, but additionally, we have here a common stream on top of it that comes from the message split. Right, and so you can build from that more general framework that holds for general K users, and you can show that the general framework is always such that SDMA, multicasting, NOMA, and this architecture here, this what we call one-layer rate splitting, is a particular instance of a more general framework. Right, so with this, once we have all that, we can start calculating what is the degrees of freedom or multiplexing gain that we have with NOMA, SDMA, and RSMA. And we can do this for different type of DOF, some degrees of freedom, max mean fair degrees of freedom, and so on. And so what we can show is that if you do NOMA, you achieve a lower or the same sum multiplexing gain as doing as SDMA. You can achieve either higher or lower max mean fair multiplexing gain compared to SDMA. So if your objective is to look at max mean fair, so the minimum rate among K users, then you can show that indeed NOMA can have a higher degrees of freedom, a higher slope compared to SDMA in some situation, but in some other situation could be worse. In terms of sum multiplexing gain, so we'll look at the slope of the sum rate, NOMA is always worse than SDMA, what most equal. And what you can show is that doing NOMA never achieve a sum or max mean fair multiplexing gain higher than one-layer rate splitting. Right, and keep in mind, importantly, when you do SDMA or multi-user linear precoding, you don't have any SIC at the receiver. When you have NOMA, you have G-1 SIC at the receiver. When you do rate splitting, one-layer rate splitting, you have 1 SIC at the receiver. So when we say Noma achieves no some multiplexing gain over SDMA, well, at the additional expenses of having a higher receiver complexity than SDMA. Right. So let me show you this based on some figures. This is a DOF enhancement of rate splitting versus MULP. This is the same figures as what I showed you earlier on. This is when we have imperfect CSIT, and you have a slope here that, depending on the number of users, the number of antennas, and the quality of the channel state information and transmitter, you can show that you have a slope increase. And so the slope increase leads to actually a rate increase. And interestingly, the slope is the best slope you could obtain. So is the optimal slope. And so you cannot find a scheme that would gives you a better slope than that. That's the slope that is given by rate splitting, is information theoretic optimum. Right, so if we look at degrees of freedom versus the number of SIC layer, then we can really see performance versus complexity. And so I have my two metrics here, sum DOF, so the slope of the sum rate, max mean fair DOF, that's the slope of the minimum rate among the K users. And here I have two examples with perfect CSIT, imperfect CSIT, left axis sum DOF, right axis MMF DOF, and x-axis here is the number of SIC layers, so the complexity. So as you move from left to right, you increase the receiver complexity. Now, what you can show is the following. What you want to do is to operate in this regime. You want to have high degrees of freedom and low receiver complexity. You do not want to be in the low performance, high complexity regime. And what we see is that if you do SDMA, SDMA works quite well in terms of some multiplexing gains. Here we have some specific values for the number of users and the number of antennas. But in general, SDMA has very low receiver complexity, has quite good sum multiplexing gain. The MMF, max mean fair multiplexing gain, in some situations could be relatively low. Noma, on the other hand, tends to operate more into lower multiplexing gain and higher complexity. You're really into this regime here. And in the worst case, when you have a single group here, you really are in a high complexity regime at the receiver, and you achieve relatively low multiplexing gain. Rate splitting, you have one SIC at the receiver, but you achieve a degrees of freedom that is at least equal or better than any other multiple access schemes. If you move to imperfect CSIT, because of the optimality of rate splitting, when you have imperfect CSIT, you see the gap is further increasing. And so you have one SIC, so you increase the complexity compared to SDMA, but you have also an increase in the DOF. In contrast with Noma, that tends to operate at much lower DOF and higher complexity. So here, this just to show you that you could have only one SIC at the receiver and achieve much better multiplexing gain than MULP and Noma. And so that's quite attractive. So just given the time limitation, let me move on a bit. This is something else, is the degrees of freedom, max mean fair degrees of freedom versus the number of users. And so this is often advertised in the Noma literature as something that is really good for Noma, is essentially being able to serve a larger number of users. Even though you may have fewer antennas, but you are able to serve a larger number of users. And this is true to some extent, that indeed, for instance, if you have 6 antennas here and you want to serve large number of users, if you want to serve 8 users, you will really struggle with MULP, with SDMA, because you would have too many users to serve and you have too few antennas. So if you use Noma, one of the two Noma techniques here with only one group, for instance, if you want to achieve a slope of 0.1, you could serve 10 users. But to do that, you would need to have 9 SICs at the receiver. So you would have one group with 10 users, and one of those users would have to decode the message of all the other users, who would have to implement 9 SICs. If you move to rate splitting, you could serve 15 users, achieve the same DOF, but you would do that with only one SIC. So there again, that shows you that you can serve a larger number of users with a low, and you have a lower complexity at the receiver. And the reason for that, why this gain comes from, is because you're not in a regime like SDMA, where you treat any interference as noise all the time. You're not in regimes where you fully decode interference all the time. You are in a regimes where you adjust how much interference you decode and how much you treat as noise through the split of the messages into common and private parts. So to highlight a few misconceptions of Noma, we have 4 here. And I think the first one is to believe that because Noma is capacity achieving in single antenna setup, single antenna broadcast channel, Noma would be efficient also when you have multi-antenna settings. And so as a consequence of that, a lot of the literature has tried to apply the single antenna principle of Noma to the multi-antenna settings without realizing that by doing so, you would waste the primary benefit of multi-antenna, which is the capability of transmitting multiple interference-free streams. A second misconception is to believe that because we have SIC receiver, then the rate will be enhanced because the interference is fully canceled. And this is actually incorrect. If you actually force yourself to decode interference, you have to make sure that the interference is relatively that would not work well if the interference is not strong. So you have to be very careful when you force to decode interference, what is the level of the interference that you encounter and whether forcing yourself to decode interference actually leads to a performance enhancement. The third misconception is that because Noma is compared to OMA when you have single antenna settings, there is no other comparison you can have. It's also sufficient to compare Noma with OMA in multi-antenna setting. And I think this leads to an issue, and I think to some extent a biasing of the literature, because you show Noma is better than OMA, yes, but that does not mean actually Noma is efficient. If you start comparing with SDMA and other types of techniques, you realize actually Noma in multi-antenna setting is much less efficient as what it's claimed. And the fourth misconception is to believe that because MISO-Noma is to believe that MISO-Noma is efficient in overloaded regime. It can be helpful, that's true, but it's not efficient in the sense that here you see, for instance, you could serve a much larger number or a relatively larger number of users with a significantly lower complexity at the receiver. Instead of having 9 SIC, you can have just 1 SIC. So again, that does not mean that Noma is efficient, simply because you could do much better than that based on other techniques. Right. So there are a few shortcomings of Noma, and here I try to summarize some of the common question that I receive quite often is, what prevents multi-antenna Noma from reaping the multiplexing gain of the system? And I think this is really fundamental, is the loss compared to SDMA and one-layer rate splitting comes from forcing one user to fully decode all streams in the group. This is the fundamental philosophy of Noma. And unfortunately, when you do that in multi-antenna settings, you force one user to act as the receiver of an effective single input, single output, multiple access channel, and this leads to a multiplexing gain loss. Does an increase in number of SIC always come with a reduction in the sum multiplexing gain, right? So for instance, here, I did not highlight this, but this is quite important. You see here, you have 2 Noma techniques, and you have achieved a sum multiplexing gain of 3 here, and here sum multiplexing gain of 1. So what you see is that you increase the number of SIC, you increase the receiver complexity, but your sum multiplexing gain decreases. That's rather awkward. We increase the complexity of the receiver, the least we would expect is a better performance, an increase, the same DOF or an increase in DOF. Here we have the exact opposite. And so this is, again, an anomaly of multi-antenna Noma. It comes from the fact that we force one user to decode the message of other users. This would not happen if you use rate splitting, for instance. A non-orthogonal transmission strategy inefficient for multi-antenna? No, they can be very good. And RSMA is a typical example of this. You can use SIC, but you're not in a regime where you force yourself to decode the message, all the streams. You don't force one user to decode the streams of all other users. So this basic principle of forcing one user in each group to fully decode the message of the other users, I think is very inefficient in multi-antenna settings. And multi-user linear precoding and RSMA do not do that. Multi-user linear precoding treat interference as known, so there is no decoding at the receiver of interference streams. And rate splitting multiple access, if you take that scheme here, does not do that either. Rate splitting builds upon multi-user linear precoding such that whenever the interference here is non-negligible compared to the noise, then it's taken care by the common stream. And so each user will decode the SE, will effectively partially decode the interference, but will not always be enforced to fully decode the message of another user. Right, so this is to highlight. And so there is, as I said, there is a relationship between Noma, rate splitting, and SDMA. Rate splitting in general is a super scheme that encompasses all those sub schemes. But you could have sub-strategies of the rate splitting multiple access, like the one-layer rate splitting that use only one SIC that is a superset of SDMA, but is not necessarily a superset of Noma in the K-user setting, but would give you performance enhancement over Noma and lower complexity at the receiver because it's not in a regime where you force one user to decode the message of other users. Right, so why one-layer rate splitting achieve higher multiplexing gain and lower receiver complexity than Noma? And here the key is to really build the rate splitting or the non-orthogonal transmission strategy upon SDMA, upon multi-user linear precoding. What we want is to achieve at least the same performance as SDMA, as multi-user linear precoding, so as the same as what you have in 4G and 5G, but get extra performance enhancement because you use an SIC in rate splitting. That's the least we want. We don't want something like in Noma where you increase the receiver complexity, but that comes with a performance that actually can be worse than SDMA. And so to enable that, you need flexibility at the transmitter to encode messages such that part of the messages are decoded by all the users and the remaining parts are decoded by the intended receivers. And so part of them is decoded by all the users. This is through the common stream. The remaining part decoded by the intended receiver is through the private streams. Right, so another interpretation of this is the following. When you do multi-user linear precoding or SDMA, actually you can view this as a full transmit side interference management strategy. You put all the emphasis on the transmitter to manage the interference. The receiver is relatively dumb. It's just treat interference as noise. Noma is the complete opposite. Is actually, it puts a lot of emphasis on the receiver side interference cancellation because one receiver has to fully decode and cancel interference from all the other receivers. And the rate splitting, on the other hand, try to smartly combine transmitter side interference cancellation and receiver side interference cancellation. And so that's by adjusting the power to the common and the private parts can actually softly bridge between the two extremes. You can use other type of SIC, other type of receiver. You're not bounded by SIC. You can use joint decoding, but the results in terms of multiplexing gain will not change. So all the results I showed you would still hold. And so the question is, when does it make sense to use Noma then? Well, if you look at the technical result based on degrees of freedom and multiplexing gain, you would say, well, RSMA achieved the same or higher multiplexing gain than Noma in all scenarios. And it does this with a lower number of SIC. So from this perspective, it's difficult to find any motivation to use multi-antenna Noma. Now, there could be one scenario where actually it is helpful is when the channels are really aligned or very closely aligned and the CSIT is perfect. In that case, you can show that Noma can achieve close performance or the same performance as DPC. But this is a very, very corner case that you would not expect to see much in practice because when you deploy users, it's very unlikely those users will be aligned with each other. The channels will not be aligned with each other. So just to show you some results, here you have different figures, but what I want to show you is this is a rate region. It's perfect channel state information at transmitter. And we have 4 different schemes. Blue is DPC, red is rate splitting, green is SDMA, so multi-user linear precoding, and yellow is Noma. And here we have the same channel strength for both users. And as we move from A to D, essentially we increase the angle between the 2 channels. So here the channels are relatively aligned with each other. Here the channels are orthogonal to each other. And so what you see here is actually rate splitting comes very close to DPC, despite the fact that it's only based on SIC, one SIC, and linear precoding, and would always outperform SDMA and Noma. As you increase the disparity of channel strength, so now you have 10 dB gap between the channel of user 1 and the channel of user 2, you see the shape of the rate region changes. We had here that SDMA was better than Noma. If you have 10 dB gap, now you have SDMA is not so good, and Noma in yellow is better. And you see that the red one is the rate splitting. Rate splitting always outperform both Noma and multi-user linear precoding. Always the rate region is always larger than what you get and comes closer to DPC. Right, so this is when you have random channels, perfect CSIT. Again, you see the rate splitting in red comes closer to DPC and is always larger than Noma and SDMA. This is another example where you have 10 users now, you want to have a quality of service and you have only 2 transmit antennas. So this is very overloaded regime, something that has been advertised quite a bit by the Noma literature. And if you do Noma, you could have some gain over SDMA here. You have a bit of gain, but what is the price you pay? Well, if you have 10 users, you have to use 9 SIC. You have to implement 9 SIC. If you do the pink strategy, the 1-layer rate splitting, you have only 1 SIC at the receiver and you get significant increase in rate and slope. So you see that the slope is increased, but this slope increase translates into an actual rate increase throughout the whole SNR regime. And so I will not go into all the simulation results, but there are many. And actually in all those scenarios, whether you have perfect CSIT, imperfect CSIT, whether you have some rate or max mean fairness, what you can show is that the rate splitting always outperform the Noma and the SDMA. So it comes as being more efficient and does this with a lower receiver complexity than Noma. For instance, here you have the yellow curve is Noma with 5 SIC. Here is rate splitting with 1 SIC. And so you have gains in terms of rate, you have gains in terms of fairness, gains in terms of robustness, and you only need 1 SIC. And you can have performance enhancement even over DPC. DPC is capacity achieving when we have perfect CSIT, but we don't know what's the best strategy when we have imperfect CSIT. And so this is why I'm showing here again. You can have performance enhancement over DPC when we have imperfect CSIT, and that would outperform SDMA and Noma. Right, so you could, because it's a fundamental communication theoretic schemes, you can use this into many, many different scenarios. And I just list here a few of them. Whenever you have multi-user interference, multi-antenna, essentially, it can be used. So when you have statistical CSIT, quantized feedback, massive MIMO, whether it's FDD or TDD, millimeter wave, user relaying, physical layer security, when you have intelligent surfaces, multi-cell, communication jamming, communication and sensing. There are many, many, many different scenarios, multi-beam satellite communication. So when I give a tutorial on rate splitting, then I go into all those applications, many more detail. So just to conclude, because the time is, we don't have so much time and I'm already well beyond the time. So we have to keep in mind, so what we show is that multi-antenna Noma leads to a loss in multiplexing gain and rate. That's very clear. And you could have in some scenario, some benefit over SDMA. In some scenario, you have a lower rate than SDMA. So the rate could be larger than SDMA in some scenarios, sometimes is lower, sometimes is equal. Noma, on the other hand, is always worse than rate splitting. It leads to a higher receiver complexity due to an inefficient use of SIC. So whenever you have gain over SDMA, you have to keep in mind that this comes from a cost of a very high number of SIC. And you could do much better than that by having a lower number of SIC and simply use, for instance, rate splitting. The misconception is due to a prevalent comparison with OMA, instead of comparing with other types of multi-user, multi-antenna schemes, SDMA and rate splitting, for instance. And an efficient design of next generation multiple access should be such that whenever you use a more complicated receiver, for instance, SIC, it should never lead to a performance loss compared to SDMA. So that means that you actually have to build your next generation multiple access upon SDMA so that you actually at least satisfy the performance that you have in 4G and 5G, but this extra SIC will give you performance enhancement. And this is exactly what the rate splitting does. And so in a way, it completely resolved the design limitation of Noma because it makes use of the multi-antenna in an efficient manner because it's optimal from a degrees of freedom. And it does this with a much lower number of SIC receiver. Right, so in terms of rate splitting, key aspect is to not to fully decode interference, not to treat the interference as knowing, but to do partially decode and partially treat interference as known. So you can view this as a robust interference management strategy, robust to imperfect CSIT. It's flexible to any interference level and is a powerful enabler of actually a unified multiple access because SDMA, NOMA, OMA, and all those different schemes actually sub-strategies of this rate splitting multiple access framework. And so it leads to some change into the physical layer and multiple access, medium access control layers. And so there are many advantages that I have highlighted, some of them, not all of them. And there are many research problems that could be tackled, whether you're more on the theoretical sides or more on the standardization or the implementation sides. And I want to conclude with a last note on how can we envision the future of multiple access techniques in 6G. And actually 5G had already quite a bit of discussions because we had all the multi-user MIMO, massive MIMO discussion. This is all into the SDMA kind of multiple access. We had multi-user superposed transmission. This goes into the NOMA direction, which is not so convincing and companies don't really use that. We have network assisted interference coordination. This is more at the receiver side, how you actually use advanced receiver to cancel interference. And you have this whole discussions on broadcast, multicast, unicast, mixed services. All those different study and work items actually kind of, could be leveraged to build a next generation multiple access based on rate splitting. But there is something that is missing is the message split at the transmitter that would lead to some standardization change. And so the rate splitting would have lots of application in different 6G scenarios. You can have enhanced CMBB, URLLC, machine type communication, and then also new services, sensing and communication to manage interference between sensing and communication, and also the interference between users or communication users, integrated cellular and satellite, and so on. And we discussed some of them in those papers here. So if you're interested in that, I invite you to have a look at this this new special interest group that we have on rate splitting multiple access that we created about six months or 8 months ago, early 2021. We organize a lot of tutorials on that. We have lots of papers. We list all the papers on the topic, or most of the papers on the topic. We organize workshops and special sessions. And so I really invite you to have a look at this. You will see you have tutorials also on YouTube. And if you have any questions, I will be obviously happy to answer either today or by email in the future. And with this, I would like to thank you for listening. And I'm sorry if I was a bit longer than expected.
Okay, thank you, Professor, for this valuable talk. And I think you provided relatively shocking results to the NUMA community. So it was really interesting. And I think we can use NUMA to resolve the question. So I think you just unmute, unmute yourself and ask a question. So Zoran, if you'd like to unmute yourself and ask your question, go ahead, please.
Hello, everyone. Are you listening to me?
Yes.
Yes, I can hear
Go
you.
ahead.
For the presentation and these great results that you have been working on recently, Professor Bruno. So I have two questions. The first would be, is there a connection between rate splitting and dirty coding, dirty paper coding?
I would say not really per se. I mean, you can view dirty paper coding as a form of nonlinear precoding. And so instead of using linear precoding, you use, for instance, you use nonlinear precoding. So you could approximate DPC with using, for instance, Tomlinson Arashima precoding. But DPC would be kind of a form of fully transmit side interference cancellation, right? While the rate splitting, you have this joint design of the transmitter and the receiver, so that part of the interference is canceled by the transmitter and part of it is canceled by the receiver here. Now you could combine rate splitting and DPC. And so this is actually something that we do, and I have not talked about, but this is what we have here in DPCRS, dirty paper coded rate splitting. And so what we do here is the following. Instead of encoding, let me take the architecture again. Instead of encoding here, instead of encoding the private message here using multi-user linear precoding, you could apply dirty paper coding on those private messages and still use the rate splitting to transmit the common stream. And so what would happen then is that if you have perfect CSIT, you know that DPC is capacity achieving. And so this architecture where you have DPC here would boil down to DPC whenever you have perfect CSIT. In other words, you would not allocate any power to the common stream. But as the CSIT imperfections increases, then you still leverage the DPC, but you start allocating more and more power to the common streams. And this is what we show here through that figure, is that if you have imperfect CSIT, you can combine DPC and rate splitting, and then you get the new schemes that actually outperform the rate splitting, the linear precoded rate splitting in red, and outperform DPC. So, but there is no direct relationship, I think, between the two strategies, but they could be combined.
Okay, thank you. And one more question. In your schemes, I see that always you have encoder jointly with the linear precoder. Why do you necessarily have to have encoder in the transmitter? Because sometimes when we study the schemes, sometimes we don't have this layer.
Right. So by mean encoder here, I mean
yes.
You refer to this one, right? This
yes,
encoder.
yes.
Yeah. So by here encoder here, I mean that in general you have your bits here, and you actually encode them using error correcting code, channel code, whether it's turbo, LDPC, polar codes, and you encode each of those essentially message into different streams. That's what I mean by that. And so in these talks, I have not really talked about the encoder. We have some link level simulations where we use, for instance, polar codes. But when we do the optimization of the precoders and the entire system, essentially we assume that we have Gaussian inputs. So all those streams here assume you don't have finite constellation, but you have Gaussian inputs, and you have infinite block lengths. So that's why you can use the log2 1 plus SINR expression.
So, okay. So basically you need them in practice to do realistic simulations, right? But theoretically it's not necessary.
Theoretically, you could start. So all the DOF is based on infinite block lengths and Gaussian inputs. But if you want to build this, actually, you need to have an actual channel code and actually finite constellation. And so this is not something I've talked about here in this talk. But if you're interested, I can send you some papers on that. And so there we actually designed the encoder based on polar code, and then the whole receiver here you have the polar decoder. And so on to actually simulate using link level simulations the actual encoding of the bits and decoding of the bits.
Mm-hmm.
Okay. But so
Okay.
for all those simulations here that we have here, those are based on optimization, simply assuming Gaussian signaling, infinite block length. So it's all based on log2 1 plus SNR expressions.
Okay.
Okay, there is
So
no link level.
basically, we have Gaussian inputs on the very left side, right?
Yes, you have Gaussian input, same as what you would do in Noma and in SDMA if you assume that you have the best possible channel code, essentially.
Okay. Thanks congratulations once again for the results. Thank you.
Thank you.
Thank you, Zoran, for a question. Is there any other questions from the attendees?
Yeah, this is Carlos Mosquera. Just, Bruno, one quick question from my side referring to the user scheduling,
Yes.
because this is some of an issue for all kind of schemes, but in particular for rate splitting, what would be the recommendation in principle for a overloaded system? How would you recommend to choose the users, whether it should be as far apart as possible or the channels should be aligned, at least within certain groups? Because as you mentioned, for example, Noma benefits a lot from having users with similar channels. That, of course, makes a lot of sense. But on the other side, for example, for space multiplexing, users should be farther apart. So what
Yeah.
would be your recommendation in terms of rail splitting application?
I think so. If you look at this figure, for instance, here, you have if you have DPC here, you see your sum rate. Your sum rate will be here. Probably you're going to have maybe roughly 6 bits per second per hertz, and 6 here. You're going to have around 12 or 13 bits per second per hertz here. This is for relatively aligned channels. If you move to 2 channels that are actually quite orthogonal, but they have the same channel strength, you see that they have both would achieve roughly 8, right? So I would say, in general, if you have the flexibility to pair, to choose among many users, 2 users that are orthogonal to each other, your sum rate will always increase by doing that, right? So I would say, in general, I think it's always better to have orthogonal channels in order to maximize the sum rate. So that would be my answer. The thing is, if you do SDMA, you have to go over maybe an exhaustive search. SDMA would be more sensitive to any non-orthogonality. So the rate loss will be faster with SDMA if your scheduling is not done properly, compared to something like rate splitting, which is, I think, more robust to managing the interference even when you have non-orthogonal channels. And so I think rate splitting would require a less computationally intensive scheduler. That's my feeling. And this is what we have seen a little bit when we do massive MIMO and things like this, is you can drop users and then design your precoders with rate splitting, and you would have to care less about which user you really choose or you really pair together. But even in Noma, in Noma, if, for instance, if you choose 2 users that are aligned with each other, from a sum rate perspective, there is no difference in taking 2 users or actually choosing just 1 user, because the sum rate in a given group will actually be no larger with Noma than what you get with OMA. So from a sum rate perspective, there is absolutely no benefit of using the Noma in each group. From a max-min fair perspective, so you want to maximize the minimum rate, then yes, then you would have a benefit of using Noma in that specific scenario instead of using OMA. Or you could use rate splitting. But I think if it's really aligned, I think it would be simpler to use Noma. But you would have to be constrained. You would be in a situation where your scheduler cannot choose which user to pair. You would be forced to say, okay, I have those 2 users that are really aligned, but I have to pair them together. And then you would do that. But if you had the flexibility at the scheduler level, you would unlikely pair those two users together. That's what I think.
Thank you. Yeah, that makes a lot of sense.
Okay, thank you.
Okay, is there any other questions from the attendees? If not, I have a question, Professor. I mean, from your talk, it seems like the rate splitting maximum access is, the magical answer for the multiple antenna scenario. Is there any shortcomings in the RSMA? You are, aware of?
Yes, there are shortcomings. I mean, RSMA is not beneficial in all scenarios, right? So, for instance, if you go to massive MIMO regime, if you have a TDD scenario where you have very accurate channel state information of the transmitter, you have good RF calibration of the RF chains, and you don't have pilot contamination, I think definitely simply using SDMA would be much simpler and would give you the same performance or roughly the same performance as rate splitting. So if you're in that regime, I would not use rate splitting. If you're in a regimes where now your CSI accuracy starts degrading because, for instance, you're still in the massive MIMO regime, but you have mobility and latency, then your CSI accuracy degrades, then you start seeing benefit of using rate splitting over SDMA. So the rate splitting gain really depends on the objective function, the propagation condition, the number of antenna you have versus the number of users. It depends on, and that's why whenever you apply this to many different scenarios that I mentioned here, the gain will really depend on which scenarios. You can have relatively large gain versus relatively smaller gain. The other thing is you could argue one drawback of rate splitting is that you have an encoding complexity that is higher, right? So when you take this strategy here, instead of having K streams to transmit, now you have K plus one stream. So your encoding here, instead of having, I don't know, polar codes where you encode K streams, now you have to encode K plus one stream. So this is an additional complexity. I think this is relatively, this is quite easy to manage because if you transmit 8 streams or 9 streams, I don't think it's a really big issue for the base station. And then you have the split of the messages that lead to some control signaling. So in practice, that would have to be designed if you want to have this in 6G, for instance. So I think those are the main things that I would say. Yes, I mean there's some cons of rate splitting as well.
Thank you, Professor. Is there any other questions? If not, let me conclude the session with a question, but it's like a bit far from the topic of Noma and multiple antennas. Professor, from your CV, from your experience, you worked in academia and you worked in the industry and in the standards. I think to some people, they are like contradicting actually. So you have published maybe theoretical papers talking about some rate and bounds, but then again, you've worked with the standards and you have many patents impressively that are, used in practice. So is there any correlation between the two sides? I mean, does, knowing theory will, affect your work in standardization and patents and, that, I mean, the other way around, when you done patenting, does this thing, affect your publishing, or is there any correlation or a dynamic relationship between the two sides?
Yeah, it's a very good question, and I think that remains a dilemma for many years. In short, I think the objective function in academia and in industry are different. They're quite different, and so it's not always easy to find the right intersection. When I was in industry, yeah, I mean, industry does not care about papers. That doesn't bring any money to the company, right? So what brings money is actually patent and actual technology that you push into the standard and you implement and you develop. So there was less emphasis on papers. You could publish, but there was less emphasis. If you go to academia, I think academic publication remains probably the most important metric. Good papers, I think, is the most important thing. Even though if you can show impact of your work through patents and through use of the techniques that you have developed, then is very important and is very good, obviously. But nevertheless, you have a limited time, and so it's difficult to do everything. And so I think at some point it's difficult to do both. I think you have to choose a little bit one side or the other. Even though I would like to actually have more closer collaboration sometime with industry to have further discussions, but the timeline we're talking about are also very different, and the problems that you're looking at there can be quite different. So yeah, it's not easy, but I struggle myself.
So when you know
find
the bounds, I mean,
with
this,
the ground.
I mean, when you know the theoretical bounds and the capacity bounds, I mean, do you use them in patenting, or when you like do some practical work in patenting? Does this thing like sharpen your tools or make your publishing better, in your opinion?
I think what is important in academia is you start with some fundamentals and you try to really understand what is the best thing you can do, and from there you derive good strategies that are really driven by some fundamentals. And as the technology develops, you try to understand how you can bring this into something that is realistic and feasible and implementable. For instance, in rate splitting, the one we have on the screen here, I think is quite attractive because it has only one SIC. There are other architecture of rate splitting, multiple access, that has many more SIC layers and is more complicated. So at some point, you start with something with bounds and optimality, and you start to see whether to what extent this leads to something that is implementable or practical. But keep in mind that what we call practical and implementable is not the same now as it would be in 10 years from now, right? So this change over time. So but I think it's good to keep an eye ultimately on what is practical and what is not practical. Otherwise, you could do something that is purely theoretical, purely information theoretic, for instance, and some people love doing that, and it's absolutely fine. But if you go to industry, maybe people may see this as too theoretical, where you don't capture enough, the practical aspects of the systems and all the impairments that you could have. And so, but you have to start somewhere. So I think starting from something simple where you can show some optimality and then growing from that, and incorporating more impairments and more realistic and more practical aspects, I think is might be a good things to do. Yeah. Unfortunately, when you go to industry, it's quite different, because in industry you cannot come up with simple simulation as we do here. You have to come up with something that is, compliant with, let's say, 3GPP, for instance, that includes a lot of different aspects in it. And then you facing the other problem is that you have too many parameters and you can't say much about where the gains really comes from, and you cannot really understand because you have too many parameters playing a role. So I think it's good to be able to break into building blocks and understand what is the fundamental limits of each building blocks before you put everything together.
That's really insightful. Thank you, Professor. It's really insightful answer. I thank you again, Professor, for joining us today and for your time and for this great lecture and great results. I thank the audience as well for registering with us and attending this valuable lecture. This lecture was recorded, and I will send. I'll put the lecture on our Facebook page and give you the link if you email me. And I don't know if I can get the emails of Zoom. If I do, I will send you the link of the lecture. And again, thank you, Professor, for joining us, and good night.
Thank you, Sami. Thank you, everyone. Bye-bye.
Bye.